Okay? So you can also see a lot finer grain structure, which is included in higher strength, but it's also more brittle, less ductility, okay? Now, if you quenched it, so real quick, before we go any further, we just cooled this one fast, but we didn't dunk it. And this could be more aligned with like a air cooling or normalizing. You know, this would be real slow. But if it's a cold day outside and you just let it cool off normal, so if it's, you know, 0 degrees or 10 degrees or whatever, and you walk away to let it normalize, and you bring it down to this, and you let it cool down normally to normalize, you can end up with partial bainite and partial perlite. Okay? So it's important to think your outside elements as well. Well, I better wrap it up because it is only 10 degrees outside. So we've heated it up. Now if we quench it and we bring it down to a cool temperature very, very fast, depending on whichever type of a quenching brine or medium we use, all right? Now it becomes martensite. Very strong, very hard, but very brittle and very poor ductility. This is bad stuff. Usually you're going to see a lot of cracks, a lot of problems. There's no give to it hardly whatsoever. As you can see, they're a very erratic grain structure, stress marks and so forth. However, this does have certain things, properties that you might want. So for example, something that's going to see just abrasion resistance, not a lot of impact or be holding stress. So a good example might be a piece of road equipment that is going to see a lot of material on it without pounding against the rock, okay? Or a conveyor system, something that is constantly dealing with an abrasive material, all right? You might want it to be very strong so it's abrasive resistant so it doesn't wear out. But you would like to gain some ductility so it's not as brittle. So then what you do is you heat it back up and you temper it. So you reheat it to under 1333 degrees. You slightly lower strength, but it's got better toughness. This is what you want. If you create martensite, typically you want to reheat it underneath the lower transformation, usually about 1200, and let it stress relieve, cool it off, and you're tempering it at that point. So you can see our two pieces here. You cannot go between martensite, bainite, or perlite without going through austenite first. You have to heat it first. Okay? So, why is all that so important? Is that really something that we deal with on a daily basis when we're welding? Absolutely. Okay? In your book, it has 3 different pictures of this. Okay? It's on page 79. What happens here is as you weld, it solidifies fastest on the exterior weld boundary, okay? So along the fusion face and groove face, solidifies here, and then this section in the center, slowly it'll start to solidify. So right here is where we create the greatest part of stress, internal stresses and so forth. Especially with stainless steels, you end up with centerline cracking. Also with brass and so forth, joining dissimilar metals as well. If that's the case, you might be too hot. But you start creating these grain boundaries. As it starts to cool off, the grain boundaries can be tighter and so forth. These can be considered discontinuities on a microscopic level. It's just the grain boundaries alone. Okay? Grain size effects on the metals. This is important. I would make sure that you find this in your book. Highlight the sections about it. Along with the iron carbon phase diagram on page 77, we'll talk about the coefficient of thermal expansion as well. Okay? So let me back up since we're there. The coefficient, I'm reading from the book, page 77, right-hand column. The coefficient of thermal expansion. The coefficient of thermal expansion is the amount of expansion a metal undergoes when it's heated and the amount of contraction that occurs when it's cool. The increase in the length of a bar 1 inch long when its temperature is raised 1 degree Celsius is called the linear coefficient of thermal expansion. The higher the coefficient, the greater amount of expansion. Therefore, the greater the contraction upon cooling. Expansion and contraction will be discussed in more detail under the effects of welding on metal, pages 104 to 114. And I don't know, I think we'll get there in this chapter as well. Maybe. Okay? I want you to look below that on hot shortness, highlight and understand what that is. Specifically dealing with, you'll see it a lot in aluminum. Moving on, page 79. Grain size effects on metals. Fine grained metals have good tensile strength, good ductility, and good low temperature properties. Coarse grained metals have slightly lower strength, less ductility, and but still have good high temperature properties. The way I describe this fine grain and coarse grain materials is very simple. Most of us are familiar with OSB board or like a chipboard plywood versus the old school plywood. Okay? The new finer grained OSB board plywood has all the little grain structures and pieces of wood have been put together, they've been glued and pressed. Okay? The old structures of plywood were more long grains that have been put together and pressed together. If you see many of those bent, you'll notice that usually a finer grain structure, a smoother surface, the OSB has more ductility and bend to it with great strength. The old school plywood, if you bend it and it stays like that for very long, it starts to splinter. Okay? So it's coarse grain structure versus finer grain structure. Welding effect on the grain size, the heat input, cooling rate, longer or short arcs, travel speed, all the essential variables we talked about. We know this at this point. Alloying. So, real quick, we talked about case hardening, nitriding, so forth earlier. These PowerPoints are kind of scattered around. I wish they would be a little more in line. However, so substitutional alloying versus interstitial alloying, okay? Real quick, these are your atoms, your steel atoms. If the atoms are small enough, they can fit within. This is a good example of carbon. Carbon can go within your iron atoms, your ferrite atoms, and they can help fill the voids in the meantime. They will bond to the center. Okay? This one right here, this is a substitutional alloy. So this might be a chromium. This is how we change stainless steel, right? The majority of this stuff, 12% of it's going to be chromium. More of the iron is going to come out of it. Still steel, it has iron in it and carbon, but certain grades of it. And we want to make sure that we're here. The atom that we're alloying is too big to fit within the boundary, so it substitutes itself, pulls one portion out of it. Okay? Physical properties of metals. I want you to read through that. We talked about melting point, coefficient thermal expansion. I jumped a little ahead a minute ago, I'm sorry about that. Weldability, fusibility, volatility. I want you to read through these on your own. Okay? Understand them. Very important pieces as well. And we're going to keep moving on. We still have quite a bit to cover within this chapter. So we talked about typical stresses. Bending pressure applied to force away from a straight line. So example here, deflection. Shearing, so a pulling action causing two bottles to slide once upon each other. Okay. Torsion is the twist. Fatigue by repeated stretching, twisting, compression while in service. Can be in many different directions. Okay, we're going to take a break here before we get back to plasticity.